This lesson is for FST Lesson 6-7 on designing simulations. It will be super important for students to read the entire lesson because I'm not going to go through or cover everything. Students need to be starting to read on page 402. We're going to talk about what a simulation is. So I'm just going to read an excerpt from the reading here. A simulation of a real situation is an experimental model that attempts to capture all aspects of the original situation that affects the outcomes. A simulation allows people to plan and predict. For example, crash tests, pre-election polls, fire drills, those are all examples of simulations wherein it would be impractical or just not even possible to wait for the real event in order to gather the data. Even college entrance exams have trial runs, like the PSAT simulating the SAT or the PLAN simulating the ACT. In this particular lesson, we will simulate an experiment by assigning numbers to possible outcomes. That's the key today, figuring out how you can utilize numbers to illustrate the situation. You will determine outcomes by generating random numbers, and I'm going to show you how to do that on your calculator. A set of numbers is considered random if each number has the same probability of occurring. Each pair of numbers has the same probability of occurring, and so on. When an experiment or simulation is repeated, each repetition is referred to or called a trial. So the type of simulation that we're learning this year in this class is called a Monte Carlo simulation. What that means is you'll be using repeated trials and a random number generator to produce relative frequencies, and therefore estimating probabilities from those. Students will need to be comfortable with doing basically three things on each simulation. The first one is usually the hardest. Determine how the situation will be modeled. I'll be modeling several examples for you to kind of help you learn some of the basic simulation setups. You'll also need to define or say or indicate what is a trial. What do you consider a trial in your situation, and what will be recorded or written down? Thirdly, students will need to specify how many trials should be run and how the answer will be obtained. A good rule of thumb when you're saying in your simulation how many trials there should be, the minimum you should say is always 50. I would recommend just say 100. If you do 100 trials, then you're always covered. Know that in actuality, during this lesson, I may only do 10, 20, or 50 trials, depending upon time constraints. So here's how you get a random number generator on your Inspire calculator. You'd hit the menu button, then probability, choose random, and then choose integer. You'll get a command on your screen that says randint, which stands for an abbreviated random integer. And then you have two options for how you can get your numbers generated. You can give the max and the min separated by a comma, or you can do the max and the min separated by a comma with the number of trials. And we'll use both interchangeably here. I'll show you different results if you use one versus the other. I'm going to start with a nice easy example just to get students comfortable with generating random numbers on their calculator. This is question number 2 in the homework. Here's what it says. Use the random number generator 10 times on your calculator to add two random integers between 1 and 6. Record your results. This will simulate tossing two dice 10 times. So let's talk about how you're going to generate two digits 10 times on your calculator. So you're going to give the random integer command, and we'll demonstrate this on the actual calculator here momentarily. We know we're going to go from 1 to 6 because they tell us that. And then they want us to do it 10 times. So they want us to have 10 trials. So our n there should technically be a 10. I'm going to show you three different ways of doing this question. We're going to start by just doing a 1 and then a 6 with no trials. So let's see what happens there. So I'm going to go to the calculator. I'm going to do menu, probability, random, and then I'm going to choose integer. And so we get the randint command. I'm going to do 1 and then the comma is down here and then the 6. When I hit enter on that, it's going to generate a random number. So if I want two digits generated 10 times, I would need to hit enter now 19 more times. So if you hit enter, it's going to generate random numbers and you would record your results. assuming that you pair them up as you go. I don't like that particular method. I feel like I get lost counting. It does count for you down here. I've generated 9 numbers so far, but then I have to scroll back and forth and record my results as I go. I like to be a little bit more organized than that. So what I'm going to do instead of that, I'm going to go back and highlight that command so that I don't have to do the menu all over again. If you highlight it and hit enter, you can go back, and I want to show you another option. If you do comma 2 here and hit enter, now you're going to get groups of 2, and then you just need to hit your enter button 9 more times. So here's 5 results: 2 and a 6, 1 and a 6, 4 and a 2, 6 and a 5, 2 and a 2, 6 and a 6. So that would be 5 results so far. Then we would need to record 5 more. So students should go ahead and give that a try on their calculator right now. I want to show you one other option. Again, go back when you're all done. Go back and highlight one of your commands, hit enter to rewrite it or recopy it. And instead of a 2 there, let's do a 10. And this to me would be the most efficient way of doing this question. Now you've got 10 numbers generated. If you hit enter one more time, now you can pair up the numbers. 1 with 1, 1 with 2, 5 with 6, 6 with 3, 4 with 4, 2 with 2, and there's no scrolling involved. So to me, that would be the fastest way of generating 20 numbers in pairs. So you could do the pairs individually and record 10 results, or you could do 10 twice, and that would give you the same thing. You would just pair them up vertically instead of horizontally. So hopefully that gives you some options for how you can set up or generate random numbers. So let's write down what we did here. We did random integer from 1 to 6, and we would have to do that 20 times and put them in pairs. So that's one option. So if you want to do that, you would record your results, because that's what they ask you to do in question 2. The next thing we did is we put in a comma 2, and we would have had to do that 10 times. They're in pairs already, you just record your 10 results. Another option, the last option, which was my favorite, was do 1 to 6 10 times. You only have to do that twice. And then you pair up the numbers as well. So we'd have to put in pairs again. So this would be you simulating, tossing a dice 10 times and seeing what you would get for your results. So let's say that we were looking for a particular result. We could count those up and divide by 10 because we did 10 trials. So that's random number generator. Let's move on to some other topics. Let's get into some actual simulations. So I took this particular activity out of your textbook from page 406. This is more like what you're going to see in the homework. Probabilities are determined in a variety of ways. In some situations, you might assume a probability, as when you assume a coin is fair. In other situations, you might conduct an experiment, or in this case, a simulation, and use a long-term relative frequency of an event as an estimate of the probability. In complicated situations, a simulation can be used to generate the relative frequency and therefore estimate what the probability would be. So this is a really good activity that we're going to use to describe the following situation. 2 brown-eyed parents can have a blue-eyed child if those parents carry a recessive gene for blue eyes. Assume that in these cases the probability of blue eyes is 1/4 and the probability of brown eyes is its complement 3/4. Design a simulation to estimate the probability of having exactly 1 of 3 children with brown eyes. What I like about the book here is that they do explain the steps pretty clearly. I'm going to add a little bit to it as we go. So again, one of your jobs in a Monte Carlo situation is to take that situation and assign numbers to what's going on. So we've got brown-eyed and blue-eyed kids, and we've got the probability of each. So the book encourages us, as one option, to assign numbers to the different eye colors. I'm going to assign 1, 2, and 3 to be the brown-eyed kid, and the 4 to represent a blue-eyed kid. So wouldn't that indeed still match with our probabilities? 3/4 for brown, 1/4 for blue. So the value of the number doesn't matter, it's how many of each you're using, and so that those match with the probabilities that were given. They ask you now to simulate 40 trials of 3-child families and record your results. So let's talk about how you're going to do a random integer now that we have the digits assigned. Because they told us to go from 1 to 4, our random integer is going to go from 1 to 4. They want us to do 3 child families. So probably what you'll do here is you'll do groups of 3. That's what I did. And then I had to do that 40 times because they told us to do 40 trials. So let's go ahead and try that on the calculator. I've already done this in advance, so I'm going to show you the results that I got. You may or may not get identical results to mine because again, these are random numbers. So here's my results. My first result was a 311, my next result was a 441, and so on. And so you can see all my different results. And now let's go ahead and answer the question. Now that we've got our results, I do have some check marks here because that was the answer that we're looking for. So let's look at what that's referring to. They're asking you to design a simulation to estimate the probability of having exactly 1 of 3 children with brown eyes. So if we have 1 child with brown eyes, that means the other 2 are blue eyes. So what I'm looking for is double 4s. Remember that a 4 represents a blue-eyed child. So if I want, of the 3 kids, 1 of them to be brown, that means 2 of them are blue. So I'm looking for outcomes that have a double 4. So I check-marked those in advance, or I check-marked those here in red. So anytime there's a double 4, that satisfies what I'm looking for. So now let's determine the actual probability. Now we're estimating it based on our results. So I got 1, 2, 3, 4, 5, 6, 7 outcomes that satisfied the situation out of the 40 trials that I ran. So 7 out of 40 would be my estimate of the probability. When you run your 40 simulations or 40 trials, you may or may not get a 7. You may get an 8 or a 9 or a 10 or a 12. And that's okay. That would simply be your results for your simulation. So know that you may or may not get the same answer as the person next to you. Let's try another question. This is question 6 in the homework. And let's read what it says. A family has 4 children. Assume a birth of a boy is equally likely to the birth of a girl. I think currently it's 51 to 49 in our country, so it's not equally likely, but we're going to assume that it is. First, list the sample space for the genders using B for boy, G for girl for a 4-child family. Then what is the probability that a family has 3 boys and 1 girl? That should all be review of chapter 6. Nothing new here in parts A and B. Part C is running a simulation with 50 families of 4 children. How close is the relative frequency in the simulation to the actual probability? So I need you to pause the video right now and do for sure steps A and B, and I'll pop those answers into the video here shortly. Then I will show you how I'm going to do a simulation here for part C, and we'll do that part together. So here are the outcomes for 4-child families, and then I check marked the things that answer the question. 3 boys, 1 girl. So out of the 16 outcomes, there were 4 outcomes that had 3 boys, 1 girl. So that's my probability. So I would say 1/4, and I'm just going to label that probability for my reference. So the sample space is part A, and the probability is part B. Next I'm going to show you the simulation, so for that I'm going to go to my calculator. Actually, instead of going to the calculator, we're going to just design the simulation first. Since I've got boys and girls, and I was using B's and G's, when I do a simulation, remember, I want to pick numbers. So I'm going to assign, since it's only 2 outcomes, I'm going to use the numbers 0 and 1. So I'm going to assign boys to be the 0 and girls to be the number 1. It asks me to do trials of 50, and I need 4 child families. So here's an option for you using a spreadsheet. I'm going to go to my calculator page, and I'm going to do a random integer from 0 to 1, and I'm going to do it in groups of 50. Now I don't want to do that, you need to do that on your regular calculator screen, and then you're just going to highlight it into a copy paste. To copy it, you just highlight it and do a Control C. That's for copy. And if you do a Control V, that will paste. So do this on a calculator page, highlight it and copy it, then open up a spreadsheet. And in the spreadsheet, you're going to go into the formula row and do a Control V to paste it. And we're going to do that 4 times so that we can do groups of 4. So you can see here that that's what I had in that command, random integers from 0 to 1 in groups of 50. So I'm going to copy and paste that 3 more times by doing Control V. So I've done all 4 now, and so you can see that this is one outcome here. Remember that a 0 is a boy and a 1 is a girl. So this would be an example of boy, boy, girl, boy. Next one here would be girl, girl, boy, boy. And so that goes all the way down to the 50th term. I'm not going to scroll down now because I want to show you one more way that you can easily count your results. So notice that we've only got zeros and ones. So if I add columns A, B, C, and D together, A plus B plus C plus D, what I want to look for is what they asked. They asked me to find 3 boys, 1 girl. If I'm looking for 3 boys, 1 girl, and the boys are 0, I'm looking for a sum of 1. So that would be a very easy thing for me to figure out now from my spreadsheet. So I'd count as I scroll down how many times I got a 1, because that would represent a family that had 3 zeros and 1 1. 3 zeros would be 3 boys and a 1 would be 1 girl. This one here would not count because that would be 2 boys, 2 girls. This one would be 3 girls, 1 boy. So I'm only going to count how many times I got a 1. So let's do that. I'm going to scroll down here and I'm going to count as I go. So I got 1 there, second one there, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I got 13 situations where I had 3 boys, 1 girl. Now if I run that simulation again, I might get a different result. So I'm going to write down what I got. I got 13 out of 50. That was the relative frequency of getting 3 boys and 1 girl. So that's the relative frequency. That's different from what I got when I did the probability. So remember the probability was 1/4. Relative frequency is something different. So that's okay. That's what a simulation has you do, is try to predict what the probability would be. So I'm going to show you one more type of problem using a simulation. And that's question 7. A survey of a sample of people reveals the relative frequency of left-handedness to be 10% in men and 8% in women. Use a Monte Carlo simulation to estimate the probability that at least one person in a sample of 1 man and 1 woman is left-handed. Then they want you to calculate the actual probability. So I'm going to help you with both here, and then we'll be done with this lesson. So again, we need to assign numbers to things. So I'm going to start with the 10% is the men. So I'm going to, and those are left-handed. So left-handed men, that's 10% of the time. So I'm going to say that the digits from 0 to 10 represent those. So those go together. Since we're dealing with percents here, we want to go all the way up to 100. So keep that in mind. So 8% is the women who are left-handed. So I want the digits from 1 to 8 to represent those people. So now I'm going to generate random integers, but only from 1 to 100, because again these are percentages. So whenever it's a percent, usually you're generating numbers from 1 to 100, and we want to do them in pairs because they ask you to do a sample of 1 man, 1 woman. So we're going to do in groups of 2, and then you would run however many trials you think is reasonable. A minimum reasonable number would be 50. I would recommend if this were a real simulation that we actually want to generate data for, that we would do it 100 times. So if this was a test question, I'd say run the simulation 100 times. For practical purposes, I would probably run this about 20 times just to save time. And so let's go ahead and do that. So let's say that we did this 20 times. Keep in mind that the first number is going to be the man, the second number is going to be representing the woman. So let's pretend that I did this, and I did record my results here. So I did the first 10 results when I did it 20 times. I wrote down the first 10, and that's going to represent the men. Then the second 10 is going to represent the women. So again, here it would be more reasonable for us to do many more trials than this. So remember, we're looking for situations where the digits are between 1 and 10. That would represent a left-handed man, the 10% that we're trying to look for. So 72 is not a number between 1 and 10. 28, not a number between 1 and 10, and so on. So, oh, right here I get the digit number 4. So that would satisfy a left-handed man. Same thing here, the number 1, that is a left-handed person. That's the 10% that I'm looking for. So far I've got 2 situations where I've got a left-handed man. And then here's my results for the women. Again, I'm looking for the digits 1 to 8. And that one's 13. That's bigger than 8. And yeah, so here we're not adding the digits together. We're just looking at the value of the digit. We're looking for numbers between 1 and 8, and we didn't get that. We got all numbers bigger than 13, so we didn't end up getting any of the women. So if we're trying to look for our answer now, what's the relative frequency that at least one person in a sample of 1 man and 1 woman is left-handed? We got 2 out of 20 for our relative frequency. So that would be our answer then for part A. You'd want to make sure to reduce that to lowest terms, of course. Next, let's talk about B, the actual probability. Keep in mind the way that that is worded. At least one person is a man or a woman. At least there is another way of saying or. So at least one, if it's an or question, we're really doing the ACP here. So we take A plus B minus the overlap, and that'll tell us the or. One or the other is at least one. So the probability of A, let's call that the men, so that was 10%. B was the 8%, 0.8, so we would add those together. And then the overlap, this is a new element that students may or may not be aware of, and I wrote that wrong, sorry about that. That should have been a minus there, minus the overlap. To get the overlap when you're dealing with percentages like this, you would multiply them together. Students didn't know that, and we haven't talked about that, so that's why I'm telling them now. 0.1 times 0.08 is how you would calculate the overlap when it's a percentage. So now when students calculate 0.1 plus 0.08 minus the overlap, which is the product of the two, they'll have the actual probability. And when you calculate that, you get about 17.2%. So let's just do a quick overview now of the simulations. Some simulations will involve percents, and in those simulations you should run random integers from 1 to 100 in however many groups you'd like, depending upon the question. If they ask you to do an actual probability, you may be using the ACP. If you're asked to do an intersection for ACP, you'll probably do multiplication. Another type of simulation is involving numbers like 0 and 1. Usually these would be involved with situations involving genders, boy versus girl, or coin tosses, heads versus tails. You generate numbers between 0 and 1. Another simulation is like we did with the eye color, and we generated numbers in groups of 3, and we just assigned digits to be whatever it is that we're looking for. And then again, in this case, we were looking for double 4s. And so then we counted those up based on the trials that we got.